Alright, so I'm recording. So this is the chapter 20 help session. And I've got 6 questions for us. And hopefully you find that this chapter, it should be the easiest one for the whole semester. It's mostly plug and chug questions. The long problems are in the other chapters. So let's start with this one. We're given a wire has a resistance, and then a second wire has twice the length and twice the resistivity, and we want to know what is its resistance. So hopefully by now you know that I do like these types of questions. Change a variable, what happens to another, and we know that the most important thing is to find the correct equation. And let me actually pull up my equation sheet. I forgot to pull that up. Let's see, but if somebody knows what the relevant equation is, feel free to put it in the chat while I pull up my equation sheet. All right. So there's not too much equations here for this chapter 20 on electric current here. All right. So let me open up the chat here. All right. Did anybody find a relevant equation for this one? And we can just kind of number them 1, 2, 3, 4, 5, etc. All right, so it is the second one, right? Talk about resistance. R equals rho L over A. So the way that I like to do these types of problems is write down the original equation and then write it again with whatever is changing, right? So it says we have twice the length and twice the resistivity. So we have 2 rho and then we have 2L. The area hasn't changed. So we just write it again with whatever changes, and then we can see that that gives it a factor of 4 in front. And so that means we have 4 times the original resistance. So definitely be able to do these types of problems. And also just know in general, if you change one variable, what happens to another. For instance, right, if you increase the area, right, let me use different colors here, then, the resistance decreases because they're in the denominator. But if you increase anything in the numerator, that would cause the resistance to increase. What's another way to increase resistance besides changing these variables? Besides changing rho, L, and A, what's another way to increase resistance? Any ideas? Do you see another equation that might be related to this? What's another way to increase resistance? So I'm glad you put voltage. But voltage doesn't actually change resistance, but it's good to talk about this because you might be looking at Ohm's law, right? V equals IR, and it might think, well, if you change V or I, then that might also change R. But the Ohm's law works similarly to the capacitance equation. If you remember when we did C was equal to Q over V, but we said, if you change the voltage, for example, if you have less voltage, right, it didn't mean that the capacitance was going to change. We said if you had less voltage, then it meant that that capacitor was going to store less charge. But changing the charge or voltage did not change the capacitance. So same thing with voltage, current, and resistance. Let's say we solve for R here in this equation. So we get let's see, R equals V over I, right? So you might think, well, if you increase voltage, you're going to change your resistance. But it doesn't work that way. The capacitance does not depend on Q and V. The resistance does not depend on V and I. If you increase the voltage on your resistor, right, then that just means that there's going to be more current flowing. So R does not depend on V and I. It depends on rho L A and something else too. So what I was looking for is equation number 3. Right? Equation number 3 tells us that resistance also depends on temperature. So if we write down this equation, resistance equals R naught times 1 plus, was it, alpha times temperature final minus temperature initial. But this equation tells us if you increase the temperature, then this gets bigger, this gets bigger. That means you're multiplying the original resistance by a bigger number. That's going to increase the resistance. So there's different ways to change the resistance, but definitely not by changing V or I. Everybody good with that one? Feel free to put a thumbs up, something like that. And there's questions, definitely post them. Right, this help session is for you. But in the meantime, we can move on to the next one. So this one says that there's this many electrons flowing past 1 point in 0.1 seconds. What is the current? So let's hold it smaller so that we can see both at the same time here. All right. Does anybody know what the relevant equation is for this one? Got them numbered right here. We're given the number of electrons. We're given time. We're looking for current. So the first equation, right, says that the current is a charge per time. So does that mean that we can just divide this number by 0.1 to get our final answer? Or is there something else that we have to do? So there's actually something else we have to do, right? Because this right here is not Q, right? This is N, right? This is the number of electrons. So first we have to go ahead and find charge. Remember the equation from the first chapter, right? Right here, Q equals plus or minus NE. So when we're given N, the number of electrons, first we have to find a charge. Then we can use the current equation. So current equals NE. Here we don't care about the negative because current is defined as the flow of positive charge, right? So that's one important thing to know. Right? Even though I have numerical questions, I always like to go over concepts, right? If you have a wire, we said that if let's say the electrons are flowing to the left, then that's equivalent with protons flowing to the right. And we said that the current direction would be in the direction that the protons would be flowing. Even though it's the electrons that are flowing to the left, we just say, hey, let's just imagine it's the protons that are flowing instead. And the current is to the right, so the flow of positive charges. So even though it is electrons that are flowing and the charge is negative, we really are just looking for the magnitude of that charge, because when we plug into our definition of current, we always use a positive charge because we're looking at the flow of protons. So that being said, we can multiply our N, right, 6.25 times 10 to the 18, times E, which we remember is right here, the charge of one electron or of one proton. 1.6 times 10 to the negative 19. So we're going to multiply these numbers together. And this gives us, actually, I picked the number so that this gives us exactly 1 coulomb, actually. And now we can plug that in here. So the current is going to be 1 coulomb over 0.1 seconds, which is going to be 10. And what's the unit for current? It's amperes or amps, right? So it's equivalent to coulombs per second, but the standard unit is amps. All right. Everybody good with this one? Don't hesitate to put a thumbs up so that I know that everyone's doing good. Awesome. And this next one, I want everyone to just take a second and try it on your own and put your answer in the chat. Hopefully this is the easiest one out of the bunch of 6 questions here. So everybody take a second, put in the chat, and if you miss it, it's good, right? Because it means that you're making a mistake now and that you won't make it later on a quiz or a test. So I strongly encourage you to try it. Because if you just watch me do it, then you're not getting the practice of, hey, am I going to make a mistake here or not? So as soon as you have your answer, just go ahead and put it in the chat. Just put A, B, C, D, or E. And I'll just wait a second for that. And on Wednesdays, I do have a meeting at 11 every Wednesday with my other class. So we will try to end at 10:50 just so I can take a couple minutes break before my next meeting. All right, we have a couple of answers. Did everybody have a chance to do it? All right. So, got somebody else just joined. So we are on number 3, so the other 2 were recorded. You can always go back and look at those. All right, so for this one, this one was hopefully pretty easy. I just wanted everyone to practice because sometimes people try to do it in their head and then they get it backwards. So we have the resistance of the resistor, we have the voltage of the battery, and we're looking for current. And so we know that that would be equation number 4, which is Ohm's law. Delta V equals IR, and I is delta V over R. So all we had to do is the 36 divided by the 9 to get the 4 amps. So this one is one of the easiest, but always write it out just so that you don't do something backwards. All right, so let's keep going. So this one is asking about RMS current. We're given a resistor, we're given the RMS current, and we want to find what the peak current is. So what's important here first, conceptually, is to understand, what does this mean, this RMS current, peak current. So it's good to visualize what's going on. Whenever you're asked about an RMS current, then that means that we're dealing with AC current, alternating current, right? Alternating current is current that alternates back and forth. And what we talked about is that, if you were to try to find the average value of this current, it would be 0. So instead we find this other type of average called root mean square. That way it's calculated slightly differently and it doesn't give us 0 for the average current. Now, if you have a current that alternates back and forth, then it has a peak value, right? So the peak value, which we call I naught, right? The peak current, that's I naught. So the 0 sometimes means initial, and sometimes it means max, right? Peak is the same thing as max, so keep that in mind. So it's good to visualize that that's what's going on. And so what that means is you can already start eliminating answers to make sure that you don't do things backwards. If we're looking for the peak current, if we look at this graph here, right? Peak current is always going to be greater than the RMS current, just by definition. So if there is anything that is smaller than 10, right, we can already cross them out. So that's the first thing. And then the other thing is just a plug and chug. We have right here, IRMS is the peak current divided by square root of 2. So whenever you have an RMS kind of problem, it's just going to be a simple plug and chug. But sometimes people will just do it backwards because they're just not thinking or trying to skip a step. So make sure that to find that peak current, you are actually multiplying the RMS value by square root of 2, which is the 10 milliamps times about 1.4, and that's going to give us the 14 milliamps. All right, let me see if I can think of any other question, anything conceptual here. The only other conceptual thing is just to understand the difference. To understand that because AC current is alternating like that, right? That it is represented with a sine wave. And so that means that sometimes you might be given a function, right? Like I equals 5 sine of 4t, right? You might be given a function like this. So if you are given a function, right, and you understand that, hey, we use a sine function for the current, and the peak current is always what's in front of the sine function. So you can look at this equation and say, hey, this 5 that I'm given, that must be the peak current. And then this 4 that I'm given, that must be omega. Does anybody know what omega stands for? And some people don't cover this in Physics 1 just because there's no time, but we do have omega right here. Omega is just 2 pi f. And I'm bringing this up now, even though we don't do too much with it right now in this chapter, but we will see this again when we get later to magnetism. So it's just good to already be aware that omega is a frequency, right? It's equal to 2 pi f, so it's just an angular frequency. F is a regular frequency and omega is an angular frequency. For now, you're not going to have to do too much with it, but just be aware. It has to do with, right, how often the current is oscillating back and forth, right? How many cycles per second. Any questions about any of the concepts for RMS? So the last thing, I'm still looking, if you have any questions, don't hesitate. But the last thing I forgot to draw for this, right, is if you have DC currents. Does anybody know what a graph of that would look like? If you had DC current instead of AC current? AC current is alternating. DC current does not alternate. So it doesn't go below the x-axis. That is correct. But there's no wave still. For DC current, that it's direct current, but it just means the current is not alternating, so it's just a straight line. So you have a constant current and a constant voltage. It doesn't change like the AC that changes back and forth. All right, let's keep going. If you have questions, definitely let me know. Which has more resistance, a 60 watt or 100 watt bulb that is plugged into a 110 volt outlet? So we did some similar ones last unit when we were talking about energy stored in a capacitor. And when we did energy stored in a capacitor, we had 3 equations for energy. And now when we're talking about watts, right, that's power. And if we look at our power equations, right, in this chapter, we can see that once again, we have 3 equations for power. Now, these ones all have RMS, but I think, yeah, right here, they're there. These are the ones without RMS, right? So when you use the power equation, if you are given an RMS value, then just make sure that everything is converted to RMS. But if you're just given regular non-alternating values, then you can just use equation number 5 here. So we're given 2 different powers and we're given 1 voltage, and we want to figure out which one has more resistance. So does anybody know which out of these 3 equations we're going to use? So I'm gonna number them 1, 2, and 3 for these 3. Which one do you think we're going to use? And while you do that, I'm going to help you visualize this. What's happening here, right, is we have a light bulb that is plugged into an outlet. And for both cases, we have a 110 volt outlet. We can think of it as a battery, even though an outlet is actually alternating, but that's the voltage that we're getting. All right, so which one glows brighter? You probably know from experience, right? If you have a 60 watt bulb, it's more dim, but if you have a 100 watt bulb, it's a lot more bright, right? So they do have different brightnesses, even though they have the same voltage. All right, so somebody put in the chat, we're going to use equation number 3, which is correct. So the way that you want to figure out which equation you're going to use is just like when we did with capacitors. You pick an equation that has one variable that remains constant. And in both cases, the 110 volts, the delta V is constant. So pick an equation that has delta V, and then that has the other variable that we're looking for, which is R. We're looking for R. So that's how we know we have to pick the third equation. So power equals delta V squared over R. So that's the trick, is to figure out what stays constant, what changes. That way now we know what happens when we change one variable, what happens to the other. So in this case, we're looking for resistance. We can just get resistance by itself. And we can see that the one that has the least power is the one that has the more resistance, because they're inversely proportional to each other. So it is indeed the 60 watt bulb that has more resistance, which kind of makes sense, right? Because your 100 watt bulb is brighter, but the one that has more resistance is more dim, because it's preventing the flow of charges and preventing it from glowing brighter is one way to think about it. All right, any questions about that one? We only got one more question, so this will be a slightly shorter session, although this question, there's a lot of concepts, and we don't really have any equations too much except Ohm's law, so I can hide the equation sheet. Have plenty of room for this. So we have a graph that shows current and voltage for a resistor. And we want to know, what does the resistance of the resistor do? I keep on forgetting to reword it. It's not the best wording. So what happens to resistance? All right. What happens to resistance as the voltage increases? So If you have no idea, put a question mark. If you have an idea, go ahead and put your best guess. But I do like to see question marks. It tells me, hey, people are not sure, but they're still, they're still here and following along. So we've got one guess in the chat. Does everybody else? If you don't know, just put a question mark, but just to let me know that you are here. And I think everybody's gonna learn something from this one. Because so far, I think everybody has missed it, which is good, right? I like it when people miss things. It means you're learning something. All right, so the idea here is that we're looking at ohmic versus non-ohmic devices. So devices that obey Ohm's law versus devices that don't obey Ohm's law. All right, so ohmic devices, they have a straight line when you plot I versus V. But non-ohmic devices do not have a straight line. Maybe they curve one way or another. So what we learned is that if we do have an ohmic device, then we learned that the slope of this line, right, slope is rise over run, so I over V. And we also know that resistance is V over I. We know this from Ohm's law. And so we know that, hey, M and R are inverses of each other, right? This tells us that resistance is equal to 1 over slope. They're inverses of each other. So if you keep that in mind and look at this line, this is a straight line. It only has one slope. So as the voltage is increasing here, right, the slope is not changing. It still has a constant slope because it's a straight line. All right, so slope is constant. That means that the resistance is constant. It's not changing. So people that put that it increased, you were thinking, hey, as the voltage is increasing, the current is increasing, right? When you have a resistor, the more voltage you apply, the more current is going to be flowing through that resistance. But the resistance in this case is not changing. Now, when we have a non-ohmic device, so now let me ask the same question that I just asked. Let's pretend that the graph looked like this on the right. Now tell me what's going to happen to the resistance as the voltage increases. Go ahead and vote again. Think about what is happening to the slope. And then remember that resistance and the slope are inverses of each other. So what's happening to the slope? And that's going to mean that R is doing what? R is an inverse of the slope. So what's happening to the slope in this graph right here? So the slope is decreasing, right? Because if you look at the slope, you have a steep slope here, and then it's getting less steep and less steep. So the slope is decreasing. So if you look at the fact that R is 1 over M, so you can't use R as 1 over M for the whole plot, but you can use it for one point. So it still shows you that if the slope is decreasing, right, then the R must be increasing because they're inverses of each other. So R is not constant, right? So we can put R is constant, R is not constant. So what this means is that the resistance is actually changing as you increase the voltage, but it's because it's a non-ohmic device, and it's because as you increase that voltage, it actually changes the temperature of the resistor and it changes its resistance. But it's just about understanding the graphs. All right, any questions about that? I do have a couple of follow-up questions before we finish. One follow-up question is you should be able to calculate slope. So for example, if I had numbers here, let's say, I had a point here and I had little tick marks, and this is 2 and this is 1, 2, 3, 4, right? And I asked you for this graph. I wouldn't ask you for this one, but for a straight line graph, if I would say, what is the resistance, find R, then you should be able to do that by using R is 1 over the slope and calculate the slope here, right? Slope is rise over run, so 2 up 2 over 4, right? Slope is 1/2. So 1 over 1/2, you get 2 for the resistance. So you should be able to calculate resistance from a graph by just looking at slope. We did one, I think, with a your turn or something that did that. And then the last thing I have, the last follow-up question I have is, let me zoom out just a little bit so we can do it all on the same page. Let's say I give you a graph. And it has 2 lines on it. Let's say it has an orange line and a pink line. And it's I versus V. And I want to know which, and these are both 2 different resistors. It's showing the voltage and current through those 2 different resistors. And I want to know which resistor has the highest resistance. Would you say R1 or R2? Which one has the highest resistance? So the one with the highest resistance, as we talked about over here, R equals 1 over M. The one with the smallest slope is going to have the highest resistance. So it is indeed R2 that has the highest resistance because it has the smallest slope. All right, so that is really all I have for this chapter. This is the easiest chapter for the semester. So that really should help you get 100 on the quiz, hopefully, and do well on the exam for this part. Are there any questions? All right, well, thank you so much for coming. I always like seeing a big crowd, and I will see you next time. I think the next help session is next Friday on chapter 21, which is definitely a little bit longer. I'll go ahead and stop recording, and I'll stay online until everyone signs off.